seconds we got? 10 seconds really, that's fine. Questions? Yes, sir.
In one of my previous classes, when we were dealing with propositional logic, we showed that the implication could be rewritten as ands and ors in a certain way. Why do we use the implication symbol instead of just keeping everything in ands and ors? Is it just to be shorthand?
One of the things that we'll do is we'll get to, in particular, what the question was essentially about would be along these lines. Let's see if I can get that right. All right, the idea of an algebra, it's like when we talk about that mathematics is the idea of mathematical objects and the rules that go along with them. I call them toys and rules, right? And so we have mathematical objects plus our rules that come along with it. Along with these math objects themselves are how do you handle unknown objects where you know the type. Unknown object, but you know the type, right? And normally we would just simply call this a variable. So if we would do classic, what's called elementary algebra or college algebra, as you go through it, your toys, these objects themselves, are just simply real numbers. And the idea of real numbers is any decimal. They're under particular types, if we would talk about different things, these would be the idea of any decimal number. It's really the idea of a scalar. It's a thing that needs one mathematical object descriptor that goes along with it. So things like temperature, money, height, things that just like mass, weight, speed, those things that have one particular value with it. Now, along with these things, under these objects of real numbers, we had things like, okay, what would be pi to the e power plus 2, things like that, and do different things. Like if we would go into the algebra, we take functions of them, say sine, But really, we have along with these, the idea of the rules. One of the things I haven't talked about again is the idea of same. Same is normally defined to be equality. But then we have all of our ops that go along with it. The plus, the times, the power, functional operation, as we go through those particular things. Now, with these objects, if I would simply say things like where an algebra comes into play is to find the unknown, which is where that word in particular comes from, would be things like, okay, 3x plus 1 equal 4. And one of the things that happens on an algebra is we actually have two types of equalities. And we talk about manipulations, whether we do these things in logic or not. This particular same measurement, this symbol has actually two meanings. Really, it's is equal and is equal. Question mark. It is. I'm going to assign it to be this. It is simply true. And the other one is a question. Is it? Right? And so it becomes, are they the same? And one is, they are the same. And so we use the same symbol with, how would you figure out the two as we go through it? So when we get into propositional logic, we're going to build these same sorts of things. And one of the things that we do with problems of this nature would be the idea of underneath an algebra would be the idea of simplification. But what is simplification? For what you learned in elementary algebra was expression, and it's really manipulation. So when I said things like x times x plus 1 times x minus 1, right? And you would multiply this all out, but what are you doing? You're using a law. if I would take this and distribute through, we would get these particular things, and you would notice that this is actually x times x squared minus 1 because those were a difference, right? And then we multiply by the x, and that's actually equal to x cubed minus x. These equals they are this. They're literally this according to laws that I understand that come along with this, that I'm allowed to do it and it doesn't change any problems. So as we go through these particular problems, expression manipulation, and we'll do the exact same thing with logic, is why would you pick one or the other? Because they're the same. And you're going to do this in logic, you're going to do this in sets, you're going to do this in graphs, you're going to do this in every form of math that has toys and rules. Whether you take linear algebra, this is what you do. Like, well, how do I do this? Well, you have to memorize the manipulations and you go through it. Well, why would I pick one over the other? The question usually is, well, what are you going to do? Why would you want the first one would be called factored form. Well, if this was equal to 0, I could solve it. Why would you want a polynomial form? Well, maybe I want to know the coefficients of the polynomial that I'm looking at, right? What's the degree of the polynomial? It's like all of them, the laws come into play and they mean the same, but so what you do in all forms of math are really the same thing. You just get new objects and new rules and new symbols, and then you keep going back and saying, I've got to memorize these, and this is how I manipulate. And I go through this entire process, and as long as I do it right, I won't have made a mistake. So if I have one look or somebody else has a different look, it's like, well, they might be the same. So what we've done in normal elementary algebra, every idea here, the idea of same questions. When are they the same? Are they the same? They are the same. We're going to do that. We're going to have, so really when we talk about 1.1, when we go through propositional logic, a better term would this be propositional algebra. We have new symbols, new manips, new operations, and then we go through it. But that's the reason why. It's just a technique that's used in all forms of math. Prior to the symbolic representation of unknowns of algebras, this was always difficult because all of mathematics was always questions. I wonder what a number, where if I would take that same number, add 1 to it, that same number, take 1 away from it, and then multiply those 3 quantities, what would I get? And that's how you did algebra. You would write that all out. And if it was all 0, what would that number have to be? And so we've learned, and this is one of the things that you have the verbal descriptions of things and the symbolic descriptions of things. Now, you have gone up through most of your math education with symbolic representation, but we need to be able to go back and forth on a rather easy basis, especially logic, since it's pretty much verbal descriptors. Any other questions? All right, so I used algebra, at least elementary algebra, as a template to kind of introduce the same template into 1.1. I wonder why that little spot is over there. What we're calling propositional logic. It's one of the things where if you go into some of the older books, you're going to notice things like if you go into some of the older books logic, you're not going to run into the word propositional. Propositional, I think, is in the last 50 years, and before that they were still doing logic. And logic itself, what we're going to talk about, goes back several thousand years. But really, it's just when we had our objects that we were talking about. So the mathematical object that we're going to study, just like studying numbers, arithmetic is the counting numbers or add 0 and the negatives, and you would go through all the different types of numbers, which we're going to actually do in this class as well. We're going to have all these different number sets concepts. Is going to be just simply what we're going to call propositions. So the word propositions is just a modern way of trying to, tighten up the language a little bit. But before this, logic was just simply talking about, declarative sentences. So what is a proposition? It's the declarative sentence that is true or false but not both. Which might seem awkward, but English or kind of really points out that but not both is kind of important for us to state. The English or, there are actually two types of ors. So if you're going over and you're in Shocker Hall and people would actually declare particular things and they would control what you eat and what you pick up, and you're sitting here and you're walking through and you're taking silverware and they say, oh, take a fork or a spoon, and you took them both, they would be okay. And let's say there was a dessert line and they said, take pie or cake, and you took both, they would say, what? I said pie or cake. Well, you just told me fork or spoon and I took both and you're okay, but if I take pie or cake and I took both, you're not okay with that. The answer's right. That's not the same or. So this one is, since there's two English ors that you have to usually figure out from context, the second one you would say, fine, what I really meant was, in the strict definition, is pie or cake, but not both. That's the second type of or. It's called an exclusive or. We exclude the both. And the other is an inclusive or, even though they have the exact same word and the exact same sound. All right, and you look at this and say, all right, what's a sentence? Well, it's just a sentence. It's talking of objects and properties of objects, right? So you would talk about things and then properties of those things. So I'm declaring something. So that automatically throws out what? Questions are gone. What else is thrown out? Opinions. Mark is the fastest person in the world. That's an opinion. You go through anything that you sit there and look at this and say, are you declaring something that I can just observe and say yes or no? Whether I know the answer doesn't matter. There are tarantulas in Kansas. And you'll be like, I don't know that, but it is a proposition because it's either true or false. Whether you know the answer doesn't matter. Right? So if you would simply say that, currently there is ice in the Antarctic. Well, true. Lots of thick, massive, growing year after year, actually. So when we're going through these things, as we declare what they are, it's like, okay, we'll throw certain things out. So that narrows the type of sentences we're going to talk with. All right. Now that you know this, one of the things we would do would be representation. How do you represent? First way. Right? Say it. The sky is blue. I could have written that or said it, right? That's one way of representing it. You have all the declarative things. The sky is green, the sky is blue, the sky is purple, my name is Mark, my name is John. Right? As long as it's a declarative sentence that you can say is true or false, but not both, we're good. There are 15 chairs in here. There's 24 tables. There's 25 tables. Things that you can just simply say. And that's one of the things when we get into the idea of, features, and we're eventually going to tear the sentences apart. And notice that inside these sentences, there are a subgroup that's coming from a set of things and then talking about that. Like, my name is Mark. I'll notice that there's the testing part. Markness of the thing is what makes it true or false. And so we'll eventually look inside of them a little bit. But right now, we could just simply say, write and say it. Just like numbers in algebra. You just write down the numbers. Well, what's the problem with numbers in algebra? How many numbers are there? Infinite, right? Not finite. Well, how many declarative sentences are there? Infinite, right? So you're kind of stuck a little bit and say, I can't write and say them all. But one of the things that happens in algebra is we talk about, if I can't represent all of them, could I represent a generic one? In other words, can we introduce the unknown proposition? What I'm saying is, it is a proposition. I'm just not going to tell you it, right? if there's this declarative sentence, well, what is it? I'm not going to tell you right now. What are you talking about? I'm going to keep it secret, right? And so what do we use these things? These things are going to be used as variables. And the way we normally write variables for here is, again, we use a single symbol, and we could say things like P, we could use Q, we could use R, we could use S, right? You know, etc. These all represent, every letter that you see represents a declarative sentence. I'm just not going to give it to you right now. Right? Just like when we had the letter X up above, we normally in algebra, it's a number. What number is it? I'm not telling you. But it's a number. All the things you can do to numbers, you can do to X. All the things that you can do to declarative sentences, we can do to these symbols. So hidden inside of it is an unspoken thing. Now, one of the things that happens with these variables, and normally we would have things like if I would write it, so I could use it, for example, I could say P denotes, that's normally how I write this, P denotes, and then I'll go ahead and write the sentence. What would be a predicate that starts? My name is Paul. Okay, this would be a classic way of labeling things. Normally with predicates, propositions, we use P, Q, R, S is kind of what they tend to stick with, just like X, Y, Z tends to be algebra. But normally you would say, let's pick a smart variable. Normally when you pick a variable, you pick a label according to what you think you might be talking about. So if you would go through a problem and says, oh, it's talking about bears, I saw a bear. How about we just write B? And it represents, I saw a bear, or it might represent anything. So I don't tell you what it represents. So this is a combination of variable and assignment. This is like doing something like this in algebra. X is 3. So wherever I see an X, I write 3. But sometimes I just simply write X. What does that represent? All numbers. And so we can do the same thing here. We can say that P is this, or just P is anything. One of the things that happens for algebra as well is I can also represent all numbers in a graphical way, right? On the real number line, X is somewhere in there. Well, what's kind of interesting about propositions, could they have a visual representation? If this is algebra, if this is elementary algebra representation, what about the same thing with truth values? If I say P and P is anything. Well, what is P? It's a declarative sentence that is what? True or false, but not both. Which tells me instead of like X is an infinite number, infinite possible numbers from negative infinity to positive infinity and all in between, whatever you say is going to represent what? True or false? Well, that's a lot easier. And so what we normally do is say P denotes true or false. It's its truth values. And this forms a truth table. Now in algebra, when you go to two variables, how do you represent it? These Cartesian cross products, right? How do you represent three variables graphically? Well, you have this three-coordinate system that represents, well, I can't, and the 4 I'm stuck because I can't visualize it, right? But on the other hand, truth tables, if I have P, P is either true or false. So what if I gave you 2? Say P, what if I gave you P and Q? What can P be? True or false? What can Q be? True or false? What are all possible combinations of those two things? True, 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 false, false, true, false, false. So that's the truth table for 2 things, right? What would the truth table look like for 3? What if I had P, Q, and R? they could be true, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, false, false, false. Right? How do we do this? It's you go through it, and there's going to be 8 of these. You would write, go through here and write true, 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 false, 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 false. Oops. Come on. False. This is going to be fun. False. Man, this is not going well today. So where I have my hand? Then true, true, false, false, false. I might be moving to chalk. This is driving me nuts. True, true, false, false. And then true, false, true, false, true, false, true, false. Everybody catch the pattern? So one variable has 2 outcomes. 2 variables has 4 outcomes. 3 variables has 8 outcomes. 4 variables will have 16. 5 variables? 6 variables?
64.
Everybody catch the pattern? And how do we do it? You start off with half true, half false, then half of those, half of those, half of those, right? You just keep cutting it over and over and over again, and you can form all of the values. In other words, what this is forming is every possible way of having a true-false combination. Now, here's the thing. If I would actually put sentences for P, Q, and R, once you assign it, what that means is you've actually picked one of those rows. So if I would say things like, P is my name is Mark, which is true, which means I'm one of the first 4 rows. And Q is the sky is yellow, which would be false, which would mean that it's either going to be row 3 or row 4. And if the third thing that I said was there are loungers in this room, which would be false, so it had to be true, false, false, so it's the 4th row. But all rows represent, I don't care what you say, it's going to be one of them. And we just simply go through the problem. And so those are, again, visual representations of all possible propositions. Just like we've done in every other form of math, we want to have representations of them. Symbolic, visual, and just go through the problem. All right. Now we're going to get into the whole idea of operations. One of the things I'm going to have to skip for now, most of the time when we do problems, like a new math, is that you talk about sameness right away. Sameness is actually harder than ops, so we're going to have to wait for a bit. Because it would be kind of weird to say, what do you mean by the same? Like, my name is Mark is the same as I'm a dog? Or when would those be the same? Well, you're talking about different things. So it's like, yeah, kind of. Well, what if I only talk about symbols? When are we talking about the same? So we're definitely not going to have something as strong as equality. Because normally when I use the word equal, I mean exactly the same. We're going to have a concept of same. And so we're going to pick a looser word than equal. We're going to pick it called equivalent. And since it's about logic, we will say that these are logically the same. So logically equivalent. We'll pick a softer word. But we don't have enough yet to talk about what am I measuring and what are we talking about. So for right now, we're just going to go ahead and start manipulating things. Operations are about take your objects and make new objects based upon your old objects. The first grouping of this normally is what's called unary operations. There's only one for this. What's a unary operation? Take one object and change it. What are things that you do in algebra? Absolute value. Takes one object and one object comes out. Sign, one object and one object comes out, right? So functional manipulation sometimes has one comes in, one comes out. Minus, number comes in, number comes out. So for us, the unary op is going to be, the first thing we're going to talk about is negation. Again, what's our objects? These declarative statements, these are sentences, right? So if I'm going to manipulate a sentence, what do I need to use? Sentence things, right? Words. So what do you think negation should do? Well, it should flip truth values, right? So if I say my name is Mark and it's true, if I would want to negate that, I would want to take it and turn it into a false. So how could I do that? Well, negation is simply to go through it and say, it is not the case that whatever you were talking about. So how would I, my name is Mark is true. But if I said it is not the case that my name is Mark, what have I turned my name is Mark into? A false. By throwing those English words in front, it is not the case that. So it is not the case that will flip a thing that's true into a thing that's false, and a thing that's false into a thing that's true. And so the way we normally denote this symbolically would be to say not P, and that is denoted by it is not the case that P, whatever P is. And I read it not P, because this is normally, when you normally negate, you would not out the thing that you're talking about, the testing, like Markness. So a lot of times we'll rewrite sentences. What is a negation of my name is Mark? It is not the case that my name is Mark. That's kind of long. Why don't you just say my name's not Mark? Well, that's the same, so I might as well say it that way. So you can say it the long way, and sometimes you can shorten it. That's the only one that we have for unary. The next ones are all going to be binary. Binary operations are going to work on how many objects? 2. And so for the binary operations, first one is conjunction. What conjunction looks like is P with the bridge symbol Q, and this is denoted as P, and then simply the English word and then Q. So it doesn't matter what. If I would conjunction, my name is Mark and the sky is blue, if I would do conjunction of those two things, it would be my name is Mark and the sky is blue. One of the interesting things of this is the truth values of conjunction is, if I would do, say, P and Q, that's either true, true, false, false, true, false, true, false, and then P and Q. Okay, let's talk about liars. If I tell you the truth, and I use the word and, I tell you the truth, would you say I told you the truth? Yes, we would agree with that. But on the other hand, if I would ever lie, I say a lie and I say a truth. I say a truth and I say a lie. I've lied. I don't care that you told me one truth or 1,000 truths and then have an and a lie. The entire thing is a lie. Under conjunction, false dominates. So this is called the conjunctive dominator, if we would look at it. For example, who is the multiplicative dominator of college algebra? That if you multiply anything by it is the only thing that's left.
0.
0. What's 5 times 0? 0. What's 10 times 0? 0. 0 is the we have dominators. Not everything does. Is there something that you can add to any number and just get that dominator back? No, unless you make a new form and say infinity is an object. What does not for us? It means that way, right? It means not finite. But if it was an object, which we do in certain types of math, is that we introduce infinity as an actual thing. What's 5 plus infinity? Infinity. What's infinity minus 1? Infinity. So that would be a dominator if you would have that. So false always wins under conjunction. Then we have or, which is disjunction. We actually have 2 ors. The first one is the inclusive or. Disjunction, which is P, V, Q. It's not the letter V, but it's a V symbol. And this is read as, the fun part about English, this is P or Q. And then we also have the exclusive or, which is read as P, O plus Q. which is read as P or Q, with context, and you kind of scratch your head and say, well, what if I can't tell the context? Then what you normally do is you actually would say, fine, let's be a little bit smarter about it. Let's say P or Q, but not both. So if there's ever doubt, say not both, so that you know. Honestly, English would be easier, and I always say this, maybe it'll catch on. We should have P or Q and P XOR Q. What's XOR? Exclusive OR. Right? Make a new OR, but we don't. So we just have the word OR and say figure it out. Man, how much have you done in math that's that way? And especially in this class, we will reuse symbols over and over and over and over again, like this. And in one context, it means one thing. In another context, it means a different thing. In another context, it means a different thing. Well, how do I tell? And they're all in the same thing. How do you tell? Figure it out. Just look at it and make reasonable assumptions. So the truth table of these, say PQ, true, true, false, false, true, false, true, false, P or Q is true. So if I said, now we kind of go through this thing to the idea of picking a fork and you like taking it. If you take both the fork and the spoon, I'm okay. If you take just the fork, I'm okay. Just the spoon, I'm okay. But if I said or and I really meant it, like for your health, like don't eat with your hands, the only time that this would be false would be if both are false. So this would be true, 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 false. But on the other hand, if I said, for your health, have you this type of food or this type of food, but I meant but not both, I would say if you took both, I would say bad, you broke my rules. But on the other hand, I want you to take one but not both. And if you don't take either, that's also bad. So for disjunction, the inclusive OR, who dominates? True. So under that operator, true is the disjunctive dominator. There is no dominator for exclusive OR. True, true is false. False, false is false. But true, or you need one, exactly one true, right, between the two things. That's what exclusive means. All right. Next one. So let's see. D would be implication. Symbolically, this is P arrow Q. Normally, we say the word if P, comma, then Q. See page 6 for lots of ways to say P implies Q. This is also called the conditional. Lots of ways. P only if Q. If P then Q. If P Q. P only if Q. P is sufficient for Q, but Q is necessary for P. There are lots of ways of saying that symbol. All right. The left-hand side is sufficient. The right-hand side is necessary. Well, why is that? Well, because the left-hand side is the gateway. And until that gateway is met, I don't really care about Q too much. If the gateway's not been met, Q can be whatever I want. So that's the idea of sufficiency. Why is Q necessary? Because if the gateway's met, Q has to happen. Whatever Q is what we get. Symbolically, again, PQ, true, true, false, false, true, false, true, false, P implies Q. P has been met, Q has to be met. It's necessary. P has been met, Q has to be. It's not. That means it's false. Would that make sense if you were programming? If this, then do this. Oh, I met it, and I didn't do it. That's bad. That's broken. On the other hand, what if the hypothesis isn't met? You skip it. So I don't care what Q is. It's just true. I appropriately skip, and so this would be what? True and true. False implies anything is true. And that's called a vacuous statement. And it lets me get away with this. All of my grandkids are married because I have no grandkids. Because if I have grandkids, then they're married is what I just said. If I have grandkids, then they're married. That's true. Why? I have no grandkids. Make sense? On the other hand, we have a trivial truth. A trivial truth would be row 1 and row 3 are trivial. I don't care what the hypothesis is. If Q is true, it's true. Because true implies true is true, and true implies false. Sorry, false implies true is still true. That's trivial. False implies, and then rows 3 and 4 are what's called the vacuous component again. Right? You know, these two are vacuous. False implies anything is always true. What is the one special row here? Row 2. True implies false is false. Everything else is true. You only have to worry about true implies false. That's false. Everybody else is a true statement. And it works for, again, the other example that I usually use on this is politicians. If you elect me, then I give you a chicken. I'm only a liar if you elect me and I don't give you a chicken. If you elect me and I give you a chicken, I'm a truth teller. If you elect me and I don't give you a chicken, I'm a liar. If you don't elect me and I give you chickens or don't give you chickens, I'm not a liar. I'm just the person who gives chickens or not. I said, if you elect me, I give you a chicken. You don't elect me, I still want to give a chicken. Okay, he's a chicken giver, right? Fine. I'm not a liar. My statement was, if you do, then I will. I don't care if you don't meet the hypothesis. Don't care what you do. It's true. You couldn't have lied. So the only time you know a politician has lied is if they say, if this, then this, and the first has been met. So you can get away with a lot of lies if you know you're not going to get elected. Okay? If you elect me, I shall create world peace, do wonderful things. It's like you only have to worry about it afterwards. Because beforehand, if you don't elect them, they're just the person talking. All right, last one, biconditional. That's P, arrow both ways, Q. And this is read P, if, and only if, Q. Usually for shorthand, we just write P, IFF, Q. That's a mathematical short word. IFF really means if and only if. Your hand gets tired writing if and only if, so you just say IFF. If. This one, on the other hand, is PQ. True, true, false, false, true, false, true, false. P, if and only if Q is true, false, false, true. What do I mean? I mean that they are the same thing. Normally when a person would say this statement, declarative statement, if and only if this declarative statement, that sort of statement usually is used to compare, right? It's a comparator. It's a comparator. This thing and this thing. This, if and only if this, which means their truth values better be the same. True, if and only if true, that's what you're wanting me to say. False, if and only if false, that's what you're wanting me to compare, right? So that's why true, if and only if true is true. False, if and only if false is true. But if they're of opposite truth values, true, if and only if false, that makes no sense. That's just false. So the biconditional acts as a comparison. Well, now do we have enough to possibly talk about sameness? We have an operator that compares. Maybe we should use this to figure out the idea of same. And we'll do that in 2 later sections. We'll come back and revisit that. All right, one of the things that I want everyone here to be able to do is what I call the truth table everyone should know. And what you should see is you should see PQ. And then I have all these columns that'll be separate from each other. And we go over like this. And then we have all the truth values underneath P and Q, right? You would have your true, true, your false, your true, your false, your true, your false. And then I want to have, like, what's not P? Whoops. What is not P? What is not Q? What is P and Q? What is P or Q? What is P or Q? What is P implies Q? What is P if and only if Q? So what truth table do I want you to be able to do? A single truth table that has in it every op. Right? You say, what's not P? Well, that would be what? False, false, true, true. Would be not Q. False, true, would be P and Q. True, false, false, false. Right? Any operations I'm missing?
Nope. I was just thinking that you're probably going to want to do contrapositive or converse.
Yeah, we'll talk about those as wording to be able to form them. But for now, there's the truth table. I expect all of my students who have ever gotten through this class that I could just simply drop like, oh, look, 3 years later, what's the truth table ever supposed to know? Right? And that would be the entire question. So, for example, this might be on the first exam. What's the truth table ever should know? And that's all I say. And then you make this and fill in the gaps, right? All right. One of the important features of this is just like you need to know arithmetic to be able to do algebra, to be able to go on from this point, you have to know what every one of these operations do. You need to be able to know that true implies false is the only false under the implication ever. You have to know those, not memorize TF order. You have to know why every true and every false is in this table. And you have to know it today. Why? Because by next class, we're going to use these as if you do. Yes?
The only one I'm confused about is the exclusive or.
Mm-hmm.
The very top, true.
Yeah, true is false.
Why?
Well, because the exclusive or it fields the but not both. You need exactly one. Exclusive or means exactly one. So that would be things like in a mechanical process, there's 2 alternators fitting in front of you that have been sold for this engine, and I say, pick alternator 1 or alternator 2. You grab them both, you're not going to fit them both in the car, are you? You get exclusively one. You just pick one, put it in. If you pick them both, it's like, what in the world? You can't fit 2 in this car. I said or, and I meant exclusive or, but I didn't. That's why I probably should have said zor. But that's why true or true, taking 2 things makes no sense for certain problems. And those problems, those logical problems, are ones that use the exclusive or sense. Like taking a cake or a pie, I meant one. Taking both alternators, I meant one. And it's like, well, I didn't take any alternator. A car needs an alternator. So that's the idea of why it's false, true, false. I meant take an alternator, so not taking either is bad. I meant take one alternator. Taking both is bad. You only get room for one. So we would just use the word or, but I mean exclusive. So that would be a logical application of that.
If you were just talking about binary operators between 2 elements, how many different truth tables are there?
Not very many.
Not very many.
We don't need all these ops. When we get into Boolean algebras, which revisits all of this, you can actually get by with one operation does everything. So, but using multiple words allows certain problems to be done easier. I mean, that's one of the features of math. Sometimes adding more complicated or more things can make it easier to set up the problem. All right, one of the things that we have to worry about now, and the last thing here, is precedence, order of operations. Obviously, I can take operations and mix them up with grouping symbols. And if I would look at the idea of precedence, the first thing we talked about is grouping. That would be at what I would call level 0. Then negation, I would consider that to be level 1. So if I see a grouping symbol, handle that first. That wins. Right? This is, please excuse my dear Aunt Sally. from, parentheses, exponentiation, multiplication, division, addition, subtraction. That's the order of precedence if I see college algebra. Well, the same thing has to happen here. If I would see something that looks like not P or Q implies P exclusive or R and not P and not R, or not R, right? So if this was my big, long thing, and I would say, what is the truth table for this? You have to scratch your head and say, well, who goes first? Right? I have to worry about the order of precedence. And so when we're doing order of precedence on problems, the idea of order of the operations, you would have to go through here and say, well, how is this going to work out? Now, the book says and or, and they put them at different precedent levels. That's not normal, right? The normal way of doing it is to say that and or are all at the same level. That also tells you that if they're done beside each other, you have no idea who goes first, which means that you should have used parentheses. It basically introduces the issue of distribution. When we have the distributive law, it's just plus and times. But now we have three ops, right? We have and, or, and exclusive or, and they're all considered equal. And so we're going to have distribution, and it'll act in some rather strange ways. And we'll also have distribution for implication, etc. And the next one would be implies, and the biconditional would be considered level 3. And so that would tell us that then, whoops, thought I grabbed that. That this guy here, if I would do this and I would try to make truth tables, who would I handle first? What would I all handle first? I would handle this parenthesis, right? I would handle that parenthesis. I would handle that parenthesis. Under this parenthesis, what would I have to do first? The not R first. So I would have to figure out each of those three before they even interact. I would have to say, what is P or Q? What is Q or R? What is not R? And then what is P or not R? All right, then what would you do? Then I would take care of this negation, so that would be the next thing. I would just simply negate those truth values. Then who would come? The and. The and has higher level than the imply.
What about the other negation?
Oh, yeah, sorry, that negation. Whoop, missed it. Then the and then what would be the last thing you would do? That imply. Now, a lot of people would be confused by the and the imply. They'd say, well, who goes first? I do the imply or the and? Well, and goes before it, but if there's ever any doubt, grouping wins, right? If there's ever a doubt, write your group symbols. If you doubt, and a person would read this and they say, I don't quite know what you mean, use extra parentheses. Just lay out, this is what I meant. There is no doubt now. So as you make the compound proposition truth tables, according to the rules of operations, you just go through and build inside out. And normally what I do when I do this is actually break out each of those tables one and just make it a really long. Now some people would say, go over here. Now how many variables do you see? 3, P, Q, and R. So what am I going to have to start off with? P, Q, and R, right? So true, 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 false, 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 true, true, false, false, right? And do that, and then for each of those 8 rows, build out that entire truth table. And last thing is just some terms, which is if you're given P implies Q. If you're given that, sometimes we can take another thing based on this. And normally I would say, like, if P then Q, we have 3 objects. the converse of P implies Q is Q implies P. It's a completely new compound proposition, but it's called the converse of the original. The inverse of P implies Q is not P implies not Q. And the contrapositive of P implies Q is not Q implies not P. People ask me about what does this mean about sameness? We don't even have a measure of same. I'm just saying that these objects are the converse, inverse, or contrapositive of that. So if I have an implication, we can have a converse of that implication, an inverse of that implication, or a contrapositive of that implication. The reason why we do this at all is because a lot of times we will tweak words in ways that are sometimes confusing. So if my name is Mark, then I'm teaching this class. What would be the inverse of that? If I'm teaching this class, then my name is Mark. Irregardless of same, that's just the converse. We tend to do it, so we'll give it its name. My name is not Mark, then I'm not teaching this class. If I'm not teaching this class, then my name is not Mark. So the first one was the inverse, the second one was the contrapositive of, if my name is Mark, then I'm teaching this class. We'll eventually talk about how they relate in terms of sameness, but for now they're just different, not a variation, but they are just simply a manipulation of the original. And they get their own name because they get used all the time. And we'll get to the issue of fallacies and mistakes in logic. We're going to use these words. All right, that's it.
For the bringing the example homework to class, did you want to like?
Wait. Stop. Forgot to say that. Due next class is the attendance is 1.15. Hand it in on a piece of paper at the beginning of class. That's how I'm testing your attendance. Does it need to be right? No, I just want to see your work and if you're here. Okay, so that's what I'm using for attendance. I'll do this. If I ever end class without doing this, somebody stop me and make me do it.
So is that just like problem 5?
Just problem 5. 1.1, problem 5.
And you want that on paper?
On paper to hand it in. Yep. All right. Thank you. Thank you for saying that.